All right. So chapter 2 is titled Scientific Measurements, and we start talking about what kinds of things we might want to measure. And we also kind of talk about the error associated with making measurements. Because every time a measurement's made, you have to, you might want to report the data, but everybody has to know that there are errors associated with the data. Nothing more pronounced than scientific errors than this COVID-19 thing, right? People making predictions and trying to identify so they can forecast behaviors and know what the best way to ease our angst. But it's clear that everybody knows that all of this is, some of it is hyperbole, some of it is guesswork, right? And so whenever anything is kind of given as data, we who are the receivers of the data need to recognize, okay, there's lots of errors associated with it for these reasons. And we also have to be ready to say, oh, look at that. I know that this has very little error because of X, Y, or Z. And so it's reliable, and I'm going to be able to improve my life because of it, right? So these types of things we want to be familiar with, and so we're going to kind of introduce to us a little bit about what kinds of things we measure and the errors associated with those measurements. So some of these properties, some of these things that we measure are physical properties of materials or elements, and some are chemical properties. Now, physical properties, generally the color, the size of the thing, anything that's associated with a physical reaction. A physical reaction. Now, a physical reaction is just one where you, for example, start with solid water and you go to liquid water, right? Here, this isn't a chemical reaction. I've written it and it looks very much like a chemical reaction, but all that's happening is the solid is becoming a liquid. The hydrogen and oxygens aren't rearranging themselves in any way. What do you call that when we take a solid and make it a liquid?
You just mentioned the word in the last
if I have
video.
Solid water, that's also known as ice.
This isn't suspension, right?
No, this is...
This has to do with mixing, right, and separating?
Yeah. This is
okay,
just...
So I'm getting the definition of suspension confused.
Overthinking it. This is ice, and this is water, right? So we're taking ice and we're just melting it, right? Going from solid to liquid. So this is the process of melting something, right? So it's not a chemical change. It's just a physical change. Same thing if we were going to take the liquid to a gas. That would be evaporation, right? We're not changing the way the water is interacting with the atoms within the water, right? We're changing just its state. So the state of the matter, the temperature at which it melts, the temperature at which it boils, right? All of these things are physical properties. Chemical properties are described in phrases like how reactive it is toward acid, or how it oxidizes or reduces or corrodes or tarnishes. These are all words that indicate there's a change in the material's properties, right? So now rusted iron is going to be much more brittle than metallic iron, right? So we can generally pick out the chemical changes from a list of reactions simply by looking for keywords like reacts or decomposition, decomposes, corrodes, oxidizes, these types of words. So let's think about this list of description or of changes and see if they are chemical or physical changes. So the first one there says magnesium metal is gray. We got some magnesium
Physical?
metal. That's a physical property. Very good. How about magnesium metal tarnishes in the air?
Chemical?
That's chemical, right. Tarnishing is another kind of fancy way of talking about rust, right? Magnesium and oxygen reacting to form magnesium oxide. Okay, magnesium metal melts at 922 Kelvin.
Physical?
Yeah, that's a physical property. That's just the melting point. Okay, and then magnesium reacts violently with hydrochloric acid.
That's chemical.
Yeah, that's a chemical reaction. Very good. The magnesium is reacting with the HCl and forming magnesium chloride, and hydrogen bubbles, hydrogen gas bubbles away, right? So we can see clearly a chemical reaction. All right. Here's another opportunity for us. Which of the following is a chemical property? Water is colorless. Water reacts violently with solid sodium metal. Water boils at 373 degrees Kelvin. What do you think?
B.
Yeah, the water reacts violently with sodium metal. Now, I don't know if you've ever seen that, but here we have a kiddie pool here. Can you see that kiddie pool there?
Yeah.
And up at the back behind the kiddie pool is a stand, and there's a piece of magnesium metal at the end there. And we're going to watch what happens when we drop the magnesium metal into the kiddie pool here. All right, so we get a little bit of an explosion, right? We get a little bit of an explosion showing a chemical reaction, right? A huge change. The solid piece of sodium reacts, forms a gas. That gas gets hot, lights on fire, and explodes. Okay, and we'll talk more about that in the future, but sodium on our periodic table is right here, number 11. Potassium, number 19, reacts almost the same as sodium, but just even more explosive. Lithium, not as explosive, but will light on fire when it's placed in water. And lithium-ion batteries, right? Lithium-ion batteries, if that lithium gets exposed, the electrolyte inside is very flammable. So if this gets exposed to moisture in the air or just a little bit of water, it can easily light on fire. And that's why in the news you used to hear, sometimes you still do every once in a while, about Tesla cars that just kind of light up, right? Not really a lot of people that have gotten injured or anything like that, and Tesla will replace it for you, but that is something that happens. Also, you know that in Hawaii it's hard to ship lithium-ion batteries here, fly them here, because at sometimes lithium-ion batteries have started airplanes on fire, right? And that can cause a problem if you're up in the air, right? So we have all of these chemicals, all these elements here in this column are very reactive, very reactive. And we'll talk about why that is in the future. But okay, let's see here. So here's an example of what's happening when we're taking something like water in a liquid form and changing it to water in the solid form, just changing its state. The molecules of water aren't forming different compounds, right? They're just changing how fast they're moving. So at the higher temperature, water molecules are moving around quickly, but as you cool them down, they move very slow, right? So essentially temperature is just changing how fast the molecules are moving. It's not performing chemistry in terms of changing the chemicals' properties or chemicals, the chemicals' properties. And here's a little video that we can watch that talks about melting and
Matter
evaporation.
can be found in any of four states: solid, liquid, gas, or plasma. Solid can be changed to liquid by melting. Solids can change directly to gas in a process called sublimation. Liquid is changed to gas by boiling. Gas can
All right, so we saw a picture there of some bubbles in water. What are those bubbles? Is that oxygen gas coming out of there? Is that hydrogen gas? No, that's gaseous water. The water on the bottom there gets really hot and it turns from a liquid to a gas, and because gaseous water is less dense, it floats up. It goes up really quick. And this is where you get problems when you have hot oil and a little bit of water in the oil, because the oil is less dense, therefore it will form a layer on top. It won't evaporate at the temperatures of our stove, right? So the water underneath gets heated quicker, it evaporates, and then pushes itself up, and as it pushes up through the oil will splatter out, and if it splatters out onto the flame or onto the stove, you can cause a fire, right? So a lot of people are confused into thinking that the bubbles in water vapor or boiling water is oxygen or hydrogen. It's just gaseous water, right? There's lots of things that can be bubbles. Everything can be a bubble as long as you get it hot enough and make it gas, right? Okay.
Gas can condense to liquid. Solids can be formed directly from gas by crystallization. A plasma is a group of positive ions and unbound electrons. Plasmas can be produced by energizing gases to give up electrons, as in this neon sign and fluorescent tube. The sun is also a plasma. Over 99% of the matter found in the universe is in the plasma state.
All right. So we got solid, liquid, gas. We're kind of familiar with those. And then I talked a little bit there, that video, about plasma. In this class, we're not going to talk about plasma very much. And most of us are familiar generally with solid and liquid and gas. Plasma is interesting, and there's a lot of technological advances because of our ability to take advantage of it. But you don't see anything indicating that a chemical is in a plasma form in chemical reactions. It's either just solid S, liquid L, G for gas, or AQ. Now, do you remember what AQ stands for?
Aqueous?
Aqueous. That's right, aqueous. And what does it mean? What is aqueous referring to?
I'm sorry, you'll have to review that.
Yeah, that's fine. So when I say NaCl aqueous,
Oh, yes.
what does it mean?
That there's water involved. It's in water.
That's right. We have our sodium chloride, but it's dissolved in the water. Okay, very good. All right, so here's another opportunity for us to flex our physical change, chemical change muscles. Can we pick out the physical change amongst these examples? When treated with bleach, some dyed fabrics change color. Grape juice left open in an unrefrigerated container turns sour. When heated strongly, sugar turns dark brown. In cold weather, water condenses on the inside surface of a single pane windows. When ignited with a match in open air, paper burns. What do you think? Which ones are obvious to you that are physical, or obvious that are chemical? We're looking for just the one that's physical, but any obvious ones?
Okay. Yeah, let me go through each one. I think A would be chemical.
That's right. When you have that dye and it interacts with strong bleaching agent, it oxidizes that dye, breaks it apart, changes its properties, and so it's no longer colorful. So that's a chemical change. All right. What about B?
I think I'm going to skip B for a second.
All right, that's fine.
C would be let's see, heated.
Have you ever heated?
I think that's physical, isn't it?
Yeah, well, actually, it's chemical
Oh,
change.
okay. It's
If
chemical?
Yeah, if you heat sugar long
Okay.
enough and it turns dark brown,
Right.
it eventually will
Right.
turn black into just carbon, right? So that dark brown
Okay.
change, you are oxidizing that sugar. Okay.
Okay.
What
So
about
that's,
what about
okay,
E?
so that's chemical.
Yeah, what about E?
Now with the match and open air, it burns. I think that's just physical, isn't it?
Nope. Paper burning.
That's also chemical?
Yeah. Paper
Oh,
burning.
yeah, because you mentioned we burn wood and how it changes the composition, right?
That's right. And a general idea of that reaction is something like C6H12O6. That's, a rough estimate of anything that's organic, like paper. Combine it with oxygen, and your products are going to be carbon dioxide and water. All right. Sometimes you might get just some black carbon ash. But yeah, so we're getting a change when we are burning. And that the need for the presence of oxygen is also a clue, because if you remove the oxygen, the process won't continue, right? Okay.
And then, okay, I found the physical, so
That's
B
chemical.
would,
Which one was the physical?
right, but no, B's chemical,
Yeah,
and then the physical would be D
that's right.
with the cold weather, right?
That's right. Have you ever had a cup of ice water that gets wet on the outside of the water, especially in Hawaii? Right? Where's that water coming from?
Yeah,
Where's that water coming from?
it's coming from the outside.
Yeah, it's not coming from the inside. It's not leaking out, right?
Right.
It's the
Right.
air molecules that contain water droplets, little tiny water droplets, hit there, are slowed down by the cold surface, and so they accumulate. Other molecules come in, accumulate, and then you get larger droplets of water. Okay, good job. So if octane, C8H18, a major chemical in automotive fuel, is heated in a vessel in the absence of any other chemicals, bubbles appear on the bottom of the vessel. What are these bubbles likely made of? And the choices are gaseous carbon, gaseous hydrogen, gaseous octane, or gaseous butane, C4H10.
Okay.
Any ideas?
So bubbles appear on the bottom of the vessel. Okay. And what's it made of?
It's made of this octane, C8H18.
Right.
And
Yeah.
and
No, I'm reading that last sentence.
oh, the last one?
Where these bubbles likely made of.
Oh, yeah.
Okay,
right.
so it's yeah, it would be the D.
The D, gaseous butane?
Oh wait, is the whole thing butane or is it?
The whole thing
C8?
is octane.
Oh, it's octane. Okay, now gaseous octane.
That's right. C. The answer is C. So if you heat a chemical in the absence of any other chemicals and it begins to bubble, those bubbles are going to be gaseous, whatever it was, right? I mean, generally, that's what happens when you take something that's liquid and you heat it in the absence of any other chemicals, it will begin to boil. Okay, very good. When water boils on the stove, what are the bubbles that form on the bottom of the container as it boils? Oxygen, hydrogen, water, accumulated air.
Water.
Water. Very good. Great. This is a very critical question because, it's silly for us as humans to be confused about something we see so frequently. It's good to understand what's going on around us. All right. Well, I think that is a good place to stop for today. All right. So we'll pick up here next time.